Hi, everyone. Thank you for joining us in today's RecSys, the inaugural RecSys track at the AI Engineer World's Fair. So today, what I want to share about is what the future might look like when we try to merge recommendation systems and language models. So my wife looked at my slides and she's like, they're so plain. So therefore, I'll be giving the talk together with Latte and Mochi. You might have seen Mochi wandering the halls around somewhere, but there'll be a lot of doggos throughout these slides. I hope you enjoy. First, language modeling techniques are not new in recommendation systems. I mean, it started with Word2Vec in 2013. We started learning item embeddings across, from co-occurrences in user interaction sequences. And then after that, we started using GRU for rec. I don't know who here remembers recurrent neural networks, gated recurrent units. Yeah. So those were very short term, and we predict the next item from a short set of sequences. Then, of course, transformers and attention came about. And we became better on attention on long-range dependencies. So that's where we started, hey, can we just process on everything in the user sequence, hundreds, 2,000 item IDs long, and try to learn from that? And of course, now, today in this track, I wanted to share with you about 3 ideas that I think are worth thinking about: semantic IDs, data augmentation, and unified models. So the first challenge we have is hash-based item IDs. Who here works on recommendation systems? So you probably know that hash-based item IDs actually don't encode the content of the item itself. And then the problem is that every time you have a new item, you suffer from the cold start problem, which is that you have to relearn about this item all over again. And therefore, there's also sparsity, right? Whereby you have a long set of tail items that have maybe 1 or 2 interactions or even up to 10, but it's just not enough to learn. So recommendation systems have this issue of being very popularity biased, and they just struggle with cold start and sparsity. So the solution is semantic IDs that may even involve multimodal content. So here's an example of trainable multimodal semantic IDs from Kuaishou. So Kuaishou is kind of like TikTok or Xiaohongshu. It's a short video platform in China. I think it's the #2 short video platform. You might have used their text-to-video model, Kling, which they released sometime last year. So the problem they had, being a short video platform, users upload hundreds of millions of short videos every day. And it's really hard to learn from these short videos. So how can we combine static content embeddings with dynamic user behavior? Here's how they did it with trainable multimodal semantic IDs. So I'm going to go through each step here. So this is the Kuaishou model. It's a standard 2-tower network. On the left, this is the embedding layer for the user, which is a standard sequence of IDs and the user ID. And on the right is the embedding layer for the item IDs. So these are fairly standard. What's new here is that they now take in content input. So all of these slides will be available online. Don't worry about it. I'll make it available right immediately after this. And to encode visual, they use ResNet. To encode video descriptions, they use BERT. And to encode audio, they use VGG-ish. Now, the thing about the trick is this: when you have these encoder models, it's very hard to backpropagate and try to update these encoder model embeddings. So what did they do? Well, firstly, they took all these content embeddings and then they just concatenated them together. I know it sounds crazy, right? But just concat them together. Then they learn cluster IDs. So I think they shared in the paper, they had like 100 million short videos, and they learned just via k-means clustering 1,000 cluster IDs. So that's what you see over there in the model encoder, which is in the boxes at the bottom, which is the cluster IDs. So above the cluster IDs, you have the non-trainable embeddings. Below that, you have the trainable cluster IDs, which are then all mapped to their own embedding table. So the trick here is this: the model encoder, as you train the model encoder learns to map the content space via the cluster IDs, which are mapped to the embedding table, to the behavioral space. So the output is this. These semantic IDs not only outperform regular hash-based IDs on clicks and likes, right? Like, that's pretty standard. But what they were able to do was they were able to increase co-start coverage, which is of 100 videos that you share, how many of them are new. They were able to increase it by 3.6%. And also increase co-start velocity, which is, okay, how many new videos were able to hit some threshold of views. And this, they did not share what the threshold was, but being able to increase co-start and co-start velocity by these numbers are pretty outstanding. So the long story short, the benefits of semantic IDs: you can address co-start, with the semantic ID itself, and now your recommendations understand content. So later in the talk, we're going to see some amazing sharing from Pinterest and YouTube. And in the YouTube one, you see how they actually blend language models with semantic IDs, whereby it can actually explain why you might like the semantic ID because it understands the semantic ID and is able to give human-readable explanations, and vice versa. Now, the next question, and I'm sure everyone here has this challenge, the lifeblood of machine learning is data, good quality data at scale, and this is very essential for search and, of course, recommendation systems, but search is actually far more important. You need a lot of metadata, you need a lot of query expansion, synonyms, you need spell checking, you need all sorts of metadata to attach to your search index. But this is very costly and high effort to get. In the past, we used to do it with human annotations, or maybe you can try to do it automatically. But LLMs have been outstanding at this. And I'm sure everyone here is sort of doing this to some extent, using LLMs for synthetic data and labels. But I want to share with you two examples from Spotify and Indeed. Now, the Indeed paper, it's quite out. I really like it a lot. So the problem that they were trying to face is that they were sending job recommendations to users via email. But some of these job recommendations were bad. They were just not a good fit for the user, right? So they had poor user experience, and then users lost trust in the job recommendations. Imagine, and how they would indicate that they lost trust was that these job recommendations are not a good fit for me, I'm just going to unsubscribe. Now, the moment a user unsubscribes from your feed or for your newsletter, it's very, very, very hard to get them back, almost impossible. So while they had explicit negative feedback, thumbs up and thumbs down, this was very sparse. How often would you actually give thumbs down feedback? Very sparse. And implicit feedback is often imprecise. What do I mean? If you get some recommendations, but you actually don't act on it, is it because you didn't like it? Or is it because it's not the right time? Or maybe your wife works there and you don't want to work in the same company as your wife. So the solution they had was a lightweight classifier to filter bad recs. And I'll tell you why I really like this paper from Indeed, in the sense that they didn't just share their successes, but they shared the entire process and how they got there. And it was fraught with challenges. Well, of course, the first thing that makes me really like it a lot was that they started with evals. So they had their experts label job recommendations and user pairs, and from the user you have their resume data, you have their activity data, and they try to see, hey, is this recommendation a good fit? Then they prompted open LLMs, Mistral and Llama 2. Unfortunately, the performance was very poor. These models couldn't really pay attention to what was in the resume and what was in the job description, even though they had sufficient context length, and the output was just very generic. So to get it to work, they prompted GPT-4, and GPT-4 worked really well. Specifically, GPT-4 had 90% precision and recall. However, it was very costly. They didn't share the actual cost, but it's too slow. It's 32 seconds. Okay, if GPT-4 is too slow, what can we do? Let's try GPT 3.5. Unfortunately, GPT 3.5 had very poor precision. What does this mean? In the sense that of the recommendations that it said were bad, only 63% of them were actually bad. What this means is that they were throwing out 37% of recommendations, which is 1/3. And for a company that tries on recommendations and people recruiting through your recommendations, throwing out 1/3 of them that are actually good is quite a guardrail for them. This was their key metric here. And also so what they did then is they fine-tuned GPT 3.5. So you can see the entire journey, right? Open models, GPT-4, GPT-3, now fine-tuning GPT 3.5. GPT 3.5 got the precision they wanted, 0.3 precision. And it's 1/4 of GPT-4's cost and latency, right? But unfortunately, it was still too slow. It was about 6.7 seconds, and this would not work in an online filtering system. So therefore, what they did was they distilled a lightweight classifier on the fine-tuned GPT 3.5 labels. And this lightweight classifier was able to achieve very high performance, specifically 0.86 AUC ROC. I mean, the numbers may not make sense to you, but suffice to say that in an industrial setting, this is pretty good. And of course, they didn't mention the latency, but it was good enough for real-time filtering. I think less than 200 milliseconds or something. So the outcome of this was that they were able to reduce bad recommendations. They were able to cut out bad recommendations by about 20%. So initially, they had hypothesized that by cutting down recommendations, even though they were bad, you will get fewer subscriptions. It's just like sending out links, right? You might have links that are clickbait. Even though they are bad, people just click on it. And they thought that even if we cut down recommendations, even if they were bad, we will get lower application rate. But this was not the case. In fact, because the recommendations were now better, application rate actually went up by 4%. And unsubscribe rate went down by 5%. That's quite a lot. So essentially, what this means is that in recommendations, quantity is not everything. Quality makes a big difference, and quality here moved the needle quite a bit, by 5%. The other example I want to share with you is Spotify. So who here knows that Spotify has podcasts and audiobooks? Oh, okay. I guess you guys are not the target audience in this use case. So Spotify is really known for song and artists, and a lot of their users just search for songs and artists, and they're very good at that. But when they started introducing podcasts and audiobooks, how would you help your users know that, these new items are available? And of course, there's a huge-ass cold start problem. Now, it's not only cold start on item, it's now cold start on category. How do you start growing a new category within your service? And of course, exploratory search was essential to the business, right? For expanding beyond music. Spotify doesn't want to just do music songs, now they're doing audio. So the solution to that is a query recommendation system. So how did they generate new queries? Well, they have a bunch of ideas, which is, extract it from catalog titles, playlist titles, you mine it from the search logs, you just take the artist, and then you just add cover to it. And this is what they use from existing data. Now, you might be wondering, where is the LLM in this? Well, the LLM is used to generate natural language queries. So this might not be sexy, but this works really well, right? Take whatever you have with conventional techniques that work really well and use the LLM to augment it when you need it. Don't use the LLM for everything at the start. So now they have these exploratory queries. When you search for something, you still get the immediate results hit, right? So you take all of this, you add the immediate results, and then you rank these new queries. So this is why when you do a search, this is the UX that you're probably going to get right now. I got this from a paper. It may have changed recently. So you still see the item queries at the bottom, but at the top, with the query recommendations, this is how Spotify informs users without having a banner. Now we have audiobooks, now we have podcasts, right? You search for something, it actually informs you that we have these new categories. The benefit here is plus 9% exploratory queries. Essentially, 1/10 of their users were now exploring their new products. So imagine that 1/10 every day exploring their new products. How quickly would you be able to grow your new product category, right? It's actually 1.1 to the power of n. It will grow pretty fast. Long story short, I don't have to tell you about the benefits of LLM augmented synthetic data, richer, high-quality data at scale on the tail queries, right? Even on the tail queries and the tail items, and it's far lower cost and effort than is even possible with human annotation. So later, we also have a talk from Instacart who will tell us about how they use LLMs to improve their search and recommendation, their search system. Now, the last thing I want to share is this challenge, whereby right now, in a regular company, the system for ads, for recommendations, for search, they're all separate systems. And even for recommendations, the model for homepage recommendations, the model for item recommendations, the model for add to cart recommendations, the model for the thank you page recommendations, they may all be different models, right? So you can imagine this, you're gonna have many, many models, but you're gonna have, leadership expects you to keep the same amount of headcount. So then how do you try to get around this, right? You have duplicative engineering pipelines, there's a lot of maintenance costs, and improving one model doesn't naturally transfer to the improvement in another model. So the solution for this is unified models, right? I mean, it works for vision, it works for language, so why not recommendation systems? And we've been doing this for a while, this is not new. And aside, maybe the text is too small, but this is a tweet from Stripe, whereby they built a transformer-based payments fraud model, right? Even for payments, the sequence of payments, you can build a foundation model which is transformer-based. So I want to share an example of the unified ranker for search and RecSys and Netflix, right? The problem I mentioned, they have teams, they are building bespoke models for search, similar video recommendations, and pre-query recommendations, like on the search page, before you even enter a search query. High operational costs, missed opportunities from learning throughout. So their solution is a unified ranker. And they call it a unified contextual ranker, which is Unicorn. So you can see over here at the bottom, there's the user foundation model, and in it, you put in the user watch history. And then you also have the context and relevance model, where you put in the context of the videos and what they've watched. Now, the thing about this unified model is that it takes in unified input, right? So now, if you are able to find a data schema where all your use cases and all your features can use the same input, you can adopt an approach like this, which is similar to multitask learning. So the input will be the user ID, the item ID, the video or the drama or the series, the search query, if a search query exists, the country, and the task. So of course, they have many different tasks. In this example, in the paper, they have 3 different tasks, search, pre-query, and more like this. Now, what they did then was very smart imputation of missing items. So for example, if you are doing an item-to-item recommendation, you're just done watching this video, you want to recommend the next video, you have no search query. How would you impute it? Well, you just simply use the title of the current item and try to find similar items. The outcome of this is that this unified model was able to match or exceed the metrics of their specialized models on multiple tasks. Think about it. I mean, it doesn't seem very impressive, right? It may not seem very impressive. Match or exceed. It might seem, we did all this work just to match. But imagine unifying all of it, like removing the tech debt and building a better foundation for your future iterations. It's going to make you iterate faster. The last example I want to share with you is unified embeddings at Etsy. So you might think that embeddings are not very sexy, but this paper from Etsy is really outstanding in what they share in terms of model architecture as well as their system. So the problem they had was, how can you help users get better results from very specific queries or very broad queries? And if you know that Etsy inventory is constantly changing. They don't have the same products all throughout, right? It's very homegrown. So now you might be querying for something like Mother's Day gift that would almost match very few items. I think very few items would have Mother's Day gift in their description or in their title, right? And lexical embedding, the other problem is that knowledge-based embeddings, like lexical embedding retrieval, don't account for user preferences. So how do you try to address this? How they address this is with unified embedding and retrieval. So if you remember, at the start of my presentation, I talked about the Kuaishou 2-tower model, right? There's the user tower, and then there's the item tower. We will see the same pattern again. Over here, you see the product tower, right? This is the product encoder. So how they encode the product is that they use T5 models for text embeddings, right? Text item descriptions, as well as a query product log for query embeddings. What was the query that was made, and what was the product that was eventually clicked or purchased? And then over here on the left, you see the query encoder, which is the search query encoder. And they both share encoders for the tokens, which is actually the text tokens, the product category, which is a token of itself, and the user location. So what this means is that now your embedding is able to match user to the location of the product itself. And then, of course, to personalize this, they encode the user preferences via the query user scalar features at the bottom. Essentially, what were the queries that the user searched for, what did they buy previously, all their preferences. Now, they also shared their system architecture. And over here, this is the product encoder from the previous slide and the query encoder from the previous slide. But what's very interesting here is that they added a quality vector because they wanted to ensure that whatever was searched and retrieved was actually of good quality in terms of ratings, freshness, and conversion rate. And what they did is they just simply concatenated this quality vector to the product embedding vector. But when you do that for the query vector, you have to expand the product vector by the same dimension so that you can do a dot product or cosine similarity. So essentially, they just slapped on a constant vector for the query embedding, and it just works. The result, 2.6% increase in conversion across the entire site. That's quite crazy. And more than 5% increase in search purchases. If you search for something, the purchase rate increases by 5%. These are very, very, very good results for e-commerce. So the benefits of unified models, you simplify the system. Whatever you build to improve one side of the tower, improve your model, your unified model, also improves other use cases that use these unified models. That said, there may also be the alignment tax. You may find that when you try to build this, try to compress all 12 use cases into a single unified model, you may need to split it up into maybe 2 or 3 separate unified models because there's just the alignment tags. We're trying to get better at one task, actually makes the other task worse. We have a talk from LinkedIn in this afternoon block, the last talk of the block, and then we also have a talk from Netflix, which will be sharing about their unified model at the start of the next block. All right, the 3 takeaways I have for you. Think about it, consider it: semantic IDs, data augmentation, and unified models. And of course, do stay tuned for the rest of the track, for the rest of the talks in this track. Okay, that's it. Thank you. I maybe have time for one question while we have our speakers from Pinterest come up and join us. Oh, you have a question? Oh, do you mind speaking in the mic, please?
I read your very long paper that you wrote on recommendation systems and what's available today, but you didn't mention the GenRec or HST work from Meta's paper, and I was just curious why you left that out.
I didn't deliberately left that out. I think I think there were so many papers that I just didn't have time, and I just time boxed myself. I was like, okay, Eugene, you're gonna be done with this in 2 weeks, and then 2 weeks is up. That's all I have, so ship it. That's all. Yes, another question, sir.
I feel like I have read in anecdotal blog posts about how part of what people might say is some of the decline in Google search quality is a move away from explicit ranking factors and sort of an easily auditable, like ultimate ranking algorithm to something more black box and using more of those techniques. And I guess I was curious if you had an opinion on whether that seems likely to be the case or whether that is just, noise and not actually influencing the quality of the search results.
Yeah, that's a good question. Unfortunately, I don't have any insider information on why that might happen. I think we do have some Google folks here. Maybe you can ask them, but honestly, I haven't realized this, and I haven't even experienced this, the degradation. Okay. I'll tweet about it.
No, don't.
And you can pull this onto the side. No, you can pull this.
Sorry, think how to do the first one.
After that. I think. No, can I just a sec? And you can move this here. Should be here.
Sorry.
That's why. Yeah, you guys. I didn't have my speaker notes, so yeah.
Should I click this?
And I think that's what they are struggling with right now.
Oh, sorry.
Are you guys okay with doing mirror?
It should be fine.
Yeah.
It'd be a lot
Yeah,
easier.
sure.
So let's actually if we had, let's close that.
So should we for this?
Okay, watch this. I'm just gonna go ahead and update and we're gonna do mirror right now, okay? Let's go preset.
Thank you everyone for your patience. Next, we have Han and Mukuntu, machine learning engineers from Pinterest. They'll be sharing with us about how they integrated LLMs to enhance relevance scoring at Pinterest. How they combine search queries with multimodal context, and this multimodal context includes visual captions, link-based text, and user-curated signals. Over to you, Han, Mukuntu.
Yeah, thanks for the introduction. Yeah, hi everyone. Thanks for joining the talk today. We are super excited to be here and share some of the learnings we have from integrating the LLM into Pinterest search. My name is Han, and today I will be presenting with Mukunda, and we are both machine learning engineers from Search Relevance team at Pinterest. So start with a brief introduction to Pinterest. Pinterest is a visual discovery platform where pinners can come to find inspiration to create a life they love. And there are three main discovery surfaces on Pinterest: the home feed, the related pins, and search. In today's talk, we'll be focusing on search, and where the user can type in their queries and find useful, inspiring content based on their information need. And we will share how we leverage LLM to improve the search relevance. Here are some key statistics for Pinterest search. Every month, we handled over 6 billion searches with billions of pins to search from, covering topics from recipe, home decor, travel, fashion, and beyond. And at Pinterest, search is remarkably global and multilingual. We support over 45 languages and reaching pinners in more than 100 countries. These numbers highlight the importance of search at Pinterest and why we are investing in search relevance to improve users' experience. So this is an overview of how Pinterest search works at the back end. So it's similar to many recommendation systems at industry. It has query understanding, retrieval, re-ranking, and the blending stage, and finally produce relevant and engagement search feeds. And in today's talk, we'll be focusing on the semantic relevance modeling that happened at the re-ranking stage, and share about how we use LLM to improve the search relevance on the search feed. Okay, so here's our search relevance model, which is essentially a classification model. Given a search query and a pin, the model will predict how much the pin is relevant to this search query. And to measure this, we use a 5-point scale ranging from the most relevant to most irrelevant. All right, now we are gonna share some key learnings we have from using the LLM to improve Pinterest search relevance. And here are 4 main takeaways that we would like to go into more details. Lesson 1, LLMs are good at relevance prediction. So before I present the result, let me first give a quick overview of the model architecture that we are using. We concatenate the query and the pin text together and pass them into a LLM to get an embedding. So this is called cross-encoder structure, where we can better capture the interaction between the query and the pin. And then we feed the embedding from LLM into an MLP layer to produce a 5-dimensional vector, which correspond to the 5 relevance levels. And during training, we fine-tune some open source LLM using Pinterest internal data and to better adapt the model to our Pinterest content. And here, I'd like to share some results to demonstrate that the usefulness of LLM. And as a baseline, we use Search Sage, which is a Pinterest in-house content and query embedding. And so if you look at the table, you can see that the LLM has substantially improved the performance of the relevance prediction. And as we use more advanced LLMs and increase the model size, the performance keeps improving. And for example, the 8 billion Llama 3 model gives 12% of improvement over the multilingual BERT-based model, and 20% of improvement over the search stage embedding model. So the lesson here is that LLMs, they are quite good at relevance prediction. All right, lesson 2. The vision language model generated captions and the user actions can be quite used for content annotations. So to use LLM for search for relevance prediction, we need to build a text representation of each pin. And here I listed several features that we for the user curated board that the pin has been saved to, or the queries that led to the
less than a second, like a 500, 400 millisecond latency at best. There are 3 levers that we can pull in order to make the model more efficient and improve the throughput and reduce the latency for these models. Sparsification, going to the smaller model, and quantization. As Mazhar explained before, smaller models definitely have a better throughput, but our recipe is that we need to go big and then go small. If you go with a smaller model initially, it doesn't have enough capacity, it doesn't have enough reasoning power to solve the complicated task that we have. So we go with a larger model, and then we start this to the 150 billion parameter model, and then we start distilling it to the smaller model. And one of the recipe here is that we need to do the distillation step by step, and that means that we go with, for example, 8B model, then 3B model, and then 1B model. So we slowly decrease the size of the model, and we distill over and over from the previous model. And that recipe shows to be much more effective rather than basically directly going from 150 billion parameter model to 1B parameter model. Same thing for pruning. Pruning is a mathematical optimization problem. You want to either reduce the your number of heads in the transformers. You can reduce the number of MLPs. Overall, these transformer models tend proven to be very, very redundant in terms of keeping the information. So we can start pruning and removing some of these layers, or reduce basically the precision for each of the activations and parameters. However, again, if you do the pruning very aggressively at the beginning, your performance would significantly suffer. So the recipe here is also do the gradual pruning. What we do is that we start pruning the model, very small pruning to the model. We distill to the smaller model, and we do it over and over again. More pruning, more distillation, more pruning, more distillation. And as you can see from this plot, doing the gradual pruning can be as effective as basically no information loss. Whereas if you just basically do aggressive pruning at the beginning, you can have up to 1% reduction in the model quality. Another lever is quantization, going to lower precision. We are leveraging FP8 for activation and model parameters. However, doing just FP8 in all the layers hurts the performance of the model, or the quality of the model significantly. So now basically your tool would be to do mixed precision. And one of the important aspects when it comes to ranking and recommendations and overall prediction tasks is you want the model, the prediction or the probability output of the model to have a very good precision. So in the LM head at the end of the language model has to be in FP32. If you do it in FP16, BF16, or FP8, what happens is that the numbers collapse, and you don't have a very good calibration on top of that, and you cannot distinguish between different items recommended. Last part is sparsification. We can sparsify basically the attentions. The most expensive part of the transformers is attention scores. And we can leverage sparsification. Not every item needs to attend to every item. And when you know your task, when you know that this is a recommendation, these are the items that you want to, in the history, you can sparsify and not have every item attend to each other. And same goes with when you are recommending the items. Instead of recommending one item, you can recommend 50 items, 500 items at the same time. But you want to make sure that these items are not attending to each other. So you sparsify the attention scores for the output and for the query. If you put everything together, we can see that basically we can have a significant reduction in the latency. What we have done is that in 4 or 5 of our release, one release after the other, we were able to reduce the latency by 7x, and at the same time increasing the throughput, which is basically the number of queries that we can handle by one GPU, by 30x. So we are improving basically the amount of the work that the GPU is doing. At the same time, we are reducing the latency that each query is seeing. These are some of basically technical reports and papers that we published during our journey to share with the community basically our lesson learned. And that's the end of our talk. So we have some time also to answer some questions. Thank you.
Please come to the microphones if you want to ask the question. Yeah.
Thank you. Great talk. One question. How did you measure that it doesn't lose generalization power? Obviously, you've done a lot of fine-tuning, and you mentioned it works for 4 or 5 tasks instead of task-specific models. How do you know it's going to work for the next 5 tasks?
That's a good question. So we have a lot of, the answer overall is having a very comprehensive benchmarking set. We have something around like 50 to 60 benchmarking. Some of them are internal, some of them are external. For example, we leverage IF-eval to make sure that the model still follows a very good instruction. As Maziar mentioned, some of the tasks are never being part of our training data, and that's how we are measuring basically the generalization to the new domain within LinkedIn use cases, for example.
Hi, thanks for the talk. I'm wondering what a small listing website can use out of the box. Have you heard of NLWeb, which was launched recently by Microsoft? If yes, what are your views on that as a recommendation system? NLWeb.
No, I haven't actually heard of it.
No, okay, cool.
Sorry about that.
Anything for smaller ones, listing websites, say real estate listing website has like thousands of real estate listings. What are the out of the box recommendation models that people can start using?
That's the. I wish that such a model would exist. I don't really. That's why I think we started this work. We were trying to see if we can actually make it a foundation model so that you can actually solve those kinds of problems. I think there's a lot of potential for this to be able to serve a lot of the use cases that are beyond the bigger companies. But definitely, I don't know any.
I think you should check out NLWeb once.
Okay, I'll look at that.
Yeah, thanks.
Thank you for the great talk. On the slide where you mentioned you have a multi-item scoring, I'm curious, what does that effectively mean? Does it mean that you need to do multi-step decoding, or it's just one step, or just processing the logics for multiple items? What does it?
It's a multi-step. We don't want to we didn't want to go to the, for example, complication of speculative decoding or basically the decoding aspect. We wanted to have everything at the pre-fill. Okay. So what we did was that basically all the items are being sequenced, all the recommended items or potential candidates are sequenced together. But we also wanted to avoid them to attend to each other. So we leverage basically what we call it like a 4D attention mask. And we developed a special kernel actually in the SGLang and VLLM to be able to do that. And now when we have up to 500 items in your query segment, those items don't attend to each other. They only attend to the historical user and user profile information.
Okay, thank you.
Hey, great talk. So user history means many things, right? So like there is all of the jobs that they've applied to and the job postings. There are so many entities and so on. The context of the model can get quite large. How did you manage that? Did you compress it, or were there parts that you focused on?
Yeah. So we actually experimented with a lot of things. We experimented with the RAG system, so that basically when we have a query, we try to figure out what are the most closest items in your history to bring it up. We also experimented with canonical orders and some sort of weight decay on the canonical orders. It turns out that for majority of applications that we have, actually canonical order is good enough. And that kind of makes sense because recommendation systems are very biased to the freshness. Yeah. So the more recent user activity helps. One of the biggest challenge is actually this is now become more like a traditional LM problem. How do you balance the distribution of your positive and negative within the context? And I think that's become something that more like an ML engineering effort to figure out, okay, do I want more positive, more negative, like how much information I need to put in the context. Yeah.
So
Just one.
I can add one more thing to
Sure.
this. There's also another complication. When you go to the serving of these models, you don't want to break the KV caching or something that you're using in the serving. So it's going to be a little bit more complicated, more cumbersome to do something that's smarter than just putting the chronological order. So that's something that needs to be designed. So it's not something that's very obvious.
Absolutely. One more question. You guys did so many experiments, tried out so many things. How's your entire system set up? Because I'm assuming that you say quantization, but you must have tried different forms of quantization, whatnot. How do you set up the system in such a way that you can try out multiple experiments and see what works best? Can you talk a bit about that?
Yes, so Mazar touched a bit on that one. I think the one thing that we hold a very high bar for the one was automation. So our system is very automated to the extent that when you're running experimentation, actually the result of the experimented is being pushed automatically into the Excel sheet. And now, when you have such an automated system, now basically the developers are very efficient in terms of, okay, I just want to figure out different quantization. So you just change the quantization parameters, and everything else just by clicking a button happens end to end. So I think automation is the key if you want to basically really optimize for these models.
So did you build all of that automation in-house, or did you?
Yes, most of them. Well, I mean, we leverage, for example, Lightning, VLLM, SGLang. We leverage basically a lot of open source tools, but we make sure that they are integrated very well with each other and optimize basically the entire flow.
Cool. Thank you.
Thank you. Thank you again, Hamad, Mazar.
Thank you.
So we'll come back after lunch at 2. So I'll see you guys back here. Thank you.
Thank you.
Yes.
Nice to meet you. Just to let
Yeah.
you know,
Yeah.
we're pushing this to stream.
Okay.
So try to stay around the podium as much as you can. But if you had a pace, that's fine. As long as you're not like walking off into the
You mean during my talk?
Yeah, during.
Okay. Yeah. Thank you. That's true. What's up? Oh, I have more in my. Okay, I cannot really talk. until afterwards.
All right. I hope everyone has had a good lunch. Good discussions in the hallways. The hallway discussions and the after talks discussions are the best, where you get a great alpha from our speakers. So continuing from the previous sharing of Netflix's foundational model, next we have Yesu, staff research scientist at Netflix, and he'll be sharing about their big bet of building a foundational model for personalization. Yesu, please.
All right. Good afternoon. Thank you, Eugene, for the introduction. So today, I'm going to share our big bet at Netflix on personalization, namely to use one foundation model to cover all the recommendation use cases. At Netflix, we have diverse recommendation needs. This is an example homepage of one of profile on Netflix. It's a 2D layout, rows and items. Diversity comes at least 3 levels. There is first level about row. We have diverse rows. We have young rows, for example, rows on comedies, rows on action movies. We have rows about new trending, just released titles. We also have rows about, for example, titles only available on Netflix. So that's the first dimension. Second dimension is, of course, the items or entities. In addition to traditionally movie and TV shows, now we have games, we have live streaming, and we are going to add more. So our content space is expanding to very heterogeneous content types. The third level is page, right? So we have homepage, we have search page, we have a kids homepage, which is tailored very differently toward kids' interest. Mobile feed is a linear page, it's not a 2D layout, so on and so forth. So different pages are also very diverse. What happened traditionally was that these lead to naturally many specialized models that get developed over the years. Some models rank videos, some rank rows, some focus on, for example, shows user have not watched yet. Some focus on shows what a user are already engaging. And many of those models were built independently over the years. They may have different objectives, but have a lot of overlaps as well. So naturally, this lead to duplications. Duplications in our label engineering as well as feature engineering. Take the feature engineering as example. We have this very commonly used factual data about user interaction history. The factual data is the same, but over the years, many features are developed, derived out of the same facts data, like counts of different actions, counts of actions within various time window or other kind of slice and dice dimensions, similarity between the user's history titles against the target titles, unique. Lastly, just a sequence of unique show IDs to be used as a sequence feature into the model. So this list can go on and on. And a lot of those features, because they are developed independently into each model, they have slight variations, but largely very similar. So become very hard to maintain. So the challenge back then was, is this scalable? Obviously not. If we keep expanding our landscape of content type or business use cases, it's not manageable to spin up new models for each individual use cases. There's not much leverage. There's some shared components on building the feature label, but still, by and large, each model basically spinned up independently. And that also impact our innovation velocity in the terms that you don't reuse as much as you can. Instead, you just spin up new models pretty much from scratch. So this was the situation about 4 years ago, at the beginning or middle of the pandemic. So the question we asked at that time was, can we centralize the learning of user representation in one place? So the answer is yes. And we had this key hypothesis about foundation model based on transformer architecture. Concretely, two hypotheses here. One hypothesis is that through scale-up semi-supervised learning, personalization can be improved. The scaling law also applies to recommendation system as it applies to LLM. Second is that by integrating the foundation model into all systems, we can create high leverage. We can simultaneously improve all the downstream canvas-facing models at the same time. So we'll see in the following slides how we validate those hypotheses. I'll break up the overview into two subsessions. First about data and the training, and then later, second about application and serving. So about data and training. So starting from data, a very interesting aspect of building such foundation model, autoregressive transformer, is that there's a lot of analogy, but also differences sometimes between this and LLM. So we can transfer a lot of learnings, inspirations from LLM development. If we start from the very bottom layer, which is basically data cleaning and tokenization, people work with LLM understand tokenization decisions have profound impact in your model quality. So although it's the bottom layer, the decision you made there can percolate through all the downstream layers and manifest as either your model quality problem or model quality plus. So this applies to recommendation foundation model as well. Instead of, there are some differences very importantly. Instead of language tokens, which is just the one ID, here for, if we want to translate the user interaction history or sequence, each of the token is a event, interaction event from the user, right? But that event has many facets or many fields. So it's not just the one ID you can represent. There are a lot of rich information about the event. So how all of those fields can play a role in making the decision of tokenization. I think that's what we need to consider very carefully. What is the granularity of tokenization and trade off that versus the context window, for example. And through many iterations, we reach the right abstraction and interfaces that we can use to adjust our tokenization to different use cases. For example, you can imagine we have one version of tokenization used for pre-training. For fine-tuning against a specific application, we apply slightly different tokenization. So moving up from the tokenization layer, then it becomes the model layers. At high level, from bottom to top, we go through the event representation, embedding layer, transformer layer, and the objective layer. So event representation, as we just briefly touched upon, many information in the event, but at high level, you can break it down by when, where, and what. When that event happened, that's about time encoding. And where it happened, it's about physical location, your locale, country, so on and so forth, but also about device, about the canvas, or which row, which page this action happened. And then what basically is about the target entity or the title, which title you interacted with, what is the interaction, how long, and that kind of information associated with the action. So that's where we need to decide what information we need to keep, what we should drop, so on and so forth. Moving one layer above, the embedding feature transformation layer, one thing that needs to be pointed out is that for recommendation, we need to combine ID embedding learning with other semantic content information. If you only have ID embedding learn from scratch in the model, then you have problem with co-star, meaning that titles the model hasn't seen during training, it doesn't know how to deal with it at inference time. So we need to have semantic content information to be complementary to those ID embeddings. This is not a problem for LLM, but very commonly encountered the co-star problem for recommendation system. Transformer layer, I think there's no need to talk too much into this in terms of architecture choices, optimization, so on and so forth. The only thing that I want to point out is that we are using the hidden state output from this layer as our user representation, which is one of the primary goal of the foundation model is to learn a good long-term user representation. Then we need to put this into context. Then things to consider are, for example, how stable is our user representation? Given our user profile, user interaction history keep changing, how do we guarantee or maintain the stability of that representation? And what kind of aggregation we should use? You can think of broadly aggregate across the time dimension in terms of sequence dimension, or aggregate across layers. You have multiple self-attention layers, how do you aggregate that? And then lastly, do we need to do explicit adaptation of the representation based on our downstream objective to fine-tune it? So then we move to last, the very top layer, objective loss function. This is also very interesting in the sense that it's much richer than LLM. Because you can see first we use, instead of one sequence, but multiple sequences to represent the output. Because you can have a sequence of entity IDs, that's your next token prediction, softmax or sample softmax. But then we have many other facets or field of each event that can be also used as a target. Right? So it could be for things like action type, it could be some aspect of the entity's metadata, like entity type, yarn, language, so on and so forth, and also about your action, like a prediction of the duration or the device where the action happened or the time when the next user play will happen. So those are all legitimate targets or labels, depends on your use case. You can use them to do the fine tuning. Now instead of, so you can cast the problem as a multitask learning problem, multi-head or hierarchical prediction, but you can also use them just as your weights, your rewards, or your mask on the loss function. So in terms of to adapt the model to zoom in into one subcategory of user behavior you want the model to learn. Okay, so that's about the model architecture that I want to talk about. So does it scale? The first question, part of the first hypothesis we want to answer is that does a scaling law apply? And I think the answer is yes. So this is over the roughly 2 to 2.5 years, we were scaling up, and we constantly still see the gain from only on the order of 10 million profile or a few million profile to now on the order of 1 billion model parameters. We scale up the data accordingly. Now, we stop here because we can still keep going, but as you may realize that recommendation systems usually have much stringent latency cost requirement. So scaling up more requires us to also distill back. Yeah, but certainly I think this is not the end of the scaling law. Before we're wrapping up the data and training discussion, I would like to highlight some of the learnings I think quite interesting we borrow from LLM. This is not an exhaustive list, but I think very interesting to me. The top three, one is multi-token prediction. You may have seen this in the DeepSeek paper, so on and so forth. So you can, implementation-wise, you can use multi-head, multi-label, so on, different implementation flavor, but the goal is really to force the model to be less myopic, more robust to serving time shift, because you have a time gap between your training and serving, and also force the model to target long-term user satisfaction and long-term user behavior instead of just focus on next action. We have observed a very notable metrics improvement by doing that. The second is multi-layer representation, which I touched upon on the profile representation. So this is also translated from LLM side of techniques of layer-wise supervision, self-distillation, or multi-layer output aggregation. The goal here is really to make a better and more stable user representation. Lastly, this is also, should be no surprise, long context window handling from truncated sliding window to sparse attention to progressively training longer and longer sequences to eventually all of the parallelism strategies. So this is about more efficient training and maximize the learning. Okay, so shift gear to talk about the serving and applications. Before the foundation model FM, this is roughly the algo stack we have for personalization. Many data, many features, many models independently developed, each serving multiple or one canvases or applications, we call. Now, with the foundation model, we consolidate largely the data and the representation layer, especially the user representation as well as content representation in the personalization domain. Model layer as well, because model now, each application model now are built on top of FM, so become a thinner layer instead of a very standalone, full-fledged model trained from scratch. So how do the various models utilize the foundation model? There are three main approaches or consumption patterns. The first is foundation model can be integrated as a subgraph within the downstream model. Additionally, the content embeddings learned from the foundation model can be integrated as the embedding lookup layers. So downstream model is a neural network. It may already have initially some of the sequence transformer tower or graph, and then using a pre-trained foundation model subgraph to directly replace that. Second is that we can push out embeddings. This is no surprise from both content side and entity embedding as well as member embeddings. The main concern here, of course, is how frequently we want to refresh the member embeddings and how we make sure they are stable. And push them to the centralized embedding store. And this, of course, allow far more wider use cases than just personalization, because people, analytics, data scientists can also just fetch those embeddings directly to do the things that they want. Finally, user can extract the models and fine-tune it for specific applications, either fine-tune or they need to do distillation to meet the online serving requirement. Especially for those with a very strict latency requirement. To wrap up, I want to show at high level the wins we accumulated over the last 1.5 years by incorporating FM into various places. So the blue bar represents how many applications have FM incorporated. The green bar represents the A/B test wins, because in any application we may have multiple A/B tests going on there to have wins. So we indeed see high leverage of FM to bring about both A/B test wins as well as infrastructure consolidation. So I think the big bets are validated. It is a scalable solution in terms of both in terms of scaled up the model with improved quality, as well as make the whole infra consolidated and scale to new applications to be much easier. High leverage because it's a centralized learning. Innovation velocity also is faster because we allow a lot of newly launched applications to directly fine-tune the foundation model to launch the first experience. So the current directions, one is that we want to have universal representation for heterogeneous entities. This is, as you can guess, the semantic ID and along those lines, because we want to cover that. As Netflix expand into very different, very heterogeneous content types. Second is generative retrieval for collection recommendation, right? So instead of just recommend a single video, be generative at inference time and serving time. Because you have multi-step decoding, a lot of the consideration about business rules or diversity, for example, can be naturally handled in the decoding process. Lastly, faster adaptation through prompt tuning. So this is also borrowed from LLM. Can we just train some soft tokens so that at inference time we can directly swap in and out those soft tokens to prompt the FM to behave differently? So that is also a very promising direction that we are getting into. All right, that concludes my talk. Thank you for your attention and questions.
Thank you, Yesu. If you have any questions, may I invite you to come to the mics in front while we get our next speakers from Instacart to get set up.
Hi, thank you for the talk. Since you get billions of users, so except the recommendation system, maybe it can do much more, right? So what's your thought on that? Since I can just ask it to predict who's the next president in the United States. Thank you.
So I actually don't, could you explain a little bit what do you mean by beyond recommendation? Do you mean the other personalization or other things?
Yeah. Yeah, since you get kind of billion users preference, so actually that preference is also been linked to what things they'll buy or who they will vote for the next president. So do you think your foundation model has that capability to expand not only recommendation, what videos they want to look at, what others they like, or what's their opinions on anything else? Thank you.
Yes, so I think we are expanding to different, I think, entity type and also capture users' taste from both on and off our platform. I think that's a general trend that we're going to. Yes.
Great, thank you. This was really helpful. Question on, and you might not be able to share it for IP reasons, but whatever you can. Thoughts on graph models? Didn't hear a lot of that in your talks. Graphs and reinforcement learning. Any utilization there? Any benefits you saw? Any boost in performance and accuracy?
Yeah, that's a very good question. I think we have actually a dedicated team, sub-team doing graph model, especially around our knowledge graph to cover the content space, both on and off our platform in the whole entertainment ecosystem. So we use actually a lot of embeddings, for example, from the graph model to co-start. That's where I show those semantic embeddings. That's where it comes from. In terms of reinforcement learning, yes, as well, especially where we consider sparse reward that we have on users from users' action are pretty much sparse, but we want to use them to guide how, for example, we generate the whole collection. That's where we need to consider how to use those rewards to guide those process. Yeah. Sure, I will be here, and so we can also follow up. Yeah.
So, do you also use these unified representations as embedding features to downstream models? You had a slide how you use the unified model.
Yeah. So so for the embeddings learning within our model, we also expose to downstream to direct consume them. We also have, to train our unified embedding, we also have some upstream, like just, for example, the GNN embeddings. Those are also consumed to do that.
Last one, is it fast?
Yes. Hello. In your embeddings, are you just using, when someone does an action, or, sorry, in these embeddings, are you just using metadata over the video to understand what they like, or are you actually using like frame by frame of the video or second clips?
Not yet. We do have that from some other content group of our organization, but I think the trend will go there. So we are not yet into very granular like clips level or view level. We have those embeddings, but not quite yet to incorporate. Yep.
Thank you.
Thank you, Yesu. Please, another round of applause for Yesu. So next we have Tejasri and Vinesh, Director of Machine Learning and Staff Machine Learning Engineer, respectively, from Instacart. They're going to share about how they use LLMs to improve search and discovery at Instacart.
Hi, good afternoon, everyone. My name is Vinesh, and he's Tejasri. We are part of the search and machine learning team at Instacart. So today we'd like to talk to you about how we are using LLMs to transform our search and discovery. So first a little bit about ourselves. Yeah, as I mentioned, we are part of the search and discovery ML team at Instacart. And for those of you who may not be familiar with Instacart, it's the leader in online grocery in North America. And our mission is to create a world where everyone has access to the food they love and more time to enjoy it together. So coming to what we'll actually talk about today, first we'll talk about the importance of search in grocery e-commerce. Then we'll look into some of the challenges facing conventional search engines. and then actually get to the meat of the talk today, which is how we are using LLMs to solve some of these problems. Finally, we'll finish with some key takeaways from today's talk. So coming to the importance of search in grocery e-commerce, I think we've all gone grocery shopping. Customers come with long shopping lists, and it's the same on the platform as well. People are looking for tens of items, and of these, a majority of them are just restocking purchases, that is, things that the customer has bought in the past, and the remaining are items that the user is trying out for the first time. So, and the majority of these purchases come from search. So search has a dual role. It needs to both support quick and efficient, it needs to help the customer quickly and efficiently find the product they're looking for, and also enable this new product discovery. And new product discovery isn't just important for the customer, it's also great for our advertisers because it helps them showcase new products, and it's also good for the platform because overall it encourages larger basket sizes. So let's see what some problems are with our existing setup that sort of makes this hard. So to begin with, we have two classes of queries that are generally more challenging, especially from an e-commerce perspective. The first are overly broad queries. In this case, like on the left, the snacks query, where there are tons of products that map to that query. And now, because our models are trained on engagement data, if we aren't exposing these products to the user, it's hard to actually collect engagement data to them, rank them up high. So the traditional cold start problem in a way. Then, as you can see on the query on the right, we have very specific queries like unsweetened plant-based yogurt, where the user is looking for something very specific. And these queries don't happen very frequently, which means that we just don't have enough engagement data to train the models on. And while we have done quite a bit of work to sort of improve this, the challenge that we continually keep facing is that while recall improves, precision is still a challenge, especially in a pre-LLM world. The next class of problems is how do we actually support that new item discovery, as we spoke about. So when a customer walks into a grocery store, let's say into a pasta aisle, they might see new brands of pasta that they would want to try out. Along with that, they would also see pasta sauce and every other thing that's needed to make a bowl of pasta. And customers would want a similar experience on our site. We have heard multiple rounds of feedback from our customers that, hey, I can find the product that I want via search, but when I'm trying to find any other related products, it's a bit of a dead end. I would need to make multiple searches to get to where I want to. So this was a problem that we wanted to solve as well. And yeah, as I mentioned, pre-LLMs, this was a hard problem because of the lack of engagement data, etc. So let's see how we actually use LLMs to sort of solve these problems. I'll sort of talk specifically about how we use LLMs to up-level our query understanding module. Now, query understanding, as I'm sure most of you know, is the most upstream part of the search stack, and very accurate outputs are needed to sort of enable better retrieval and recall, and finally improve our ranking results. So our query understanding module has multiple models in them, like query normalization, query tagging, query classification, category classification, etc. So in the interest of time, I'll just pick a couple of models and talk about how we sort of really improve them. The first is our query to product category classifier. Essentially, we are taking a query and mapping it to a category in our taxonomy. So as an example, if you take a query like watermelon, that maps to categories like fruits, organic foods, etc. And our taxonomy has about 10,000 labels, of which 6,000 are more commonly used. So because a query can map to multiple labels, this is essentially a multi-label classification problem. And in the past, our traditional models, we actually had a couple of different models. One was a fast text-based neural network, which essentially modeled the semantic relationship between the query and the category. And then as a fallback, we had an NPMI model, which was a statistical co-occurrence model between the query and the category. Now, while these techniques work great for the head and torso queries, we had really low coverage for our tail queries because, again, we just didn't have enough engagement data to train the models on. And to be honest, we actually tried more sophisticated BERT-based models as well. And while we did see some improvement, the lack of engagement data meant that for the increased latency, we didn't see the wins that we actually hoped for. So, so this is where we actually tried to use an LLM. First, we took all of our queries, and we, along with the taxonomy, we fed it into an LLM and asked it to predict the most relevant categories for that query. Now, the output that came back was decent. Actually, when we all looked at it, it made a lot of sense. But when we actually ran an online A/B test, the results weren't as great. And one particular example that illustrates this point very well is a query like protein. Our users that come to Instacart, when they type something like protein, they're looking for maybe protein shakes, protein bars, or other protein supplements. The LLM, on the other hand, thinks that when a user types protein, they're looking for maybe chicken, tofu, or other protein foods. So this mismatch, wherein the LLM doesn't truly understand Instacart user behavior, was really the cause of the problem. So to sort of maybe improve our results, we sort of switched the problem around. We took the most commonly converting categories, or the top K converting categories for each query, and fed that as additional context to the LLM. And then I'm sort of simplifying this a bit. There's a bunch of ranking and downstream validation that happens. But essentially, that was what we did. We generated a bunch of candidates, ranked candidates, and this greatly simplified the problem for the LLM as well. And again, to illustrate this with an example, take a query like Werner's Soda. Our previous model actually identified this as a brand of fruit flavored soda, which is not incorrect, but it's not very precise either. Now, the LLM did a much better job. It identified it as a brand of ginger ale. And with this, our downstream retrieval and ranking improved greatly as well. And as you can see from the results below, especially for tail queries, we saw a big improvement. Our precision improved by over 18 percentage points, and our recall improved by over 70 percentage points, which is actually pretty significant for our tail queries. And maybe to very briefly look at our prompt, as you can see, it's very simple. We are essentially passing in the top converted categories as context. There are a bunch of guidelines about what the LLM should actually outdo, and that's it. So this was all that is needed to sort of enable this. Again, I'm simplifying the overall flow, but the general concepts are pretty straightforward. So coming to another model, the query rewrites model is actually pretty important as well from an e-commerce perspective, especially at Instacart, because not all retailers are created equal. Some have large catalogs, some have very small catalogs. The same query may not always return results. And that is where a rewrite is really helpful. For example, going from a query like 1% milk to just milk would at least return results that the customer can decide to buy or not. And again, our previous approach, which was trained on engagement data, didn't do too well. It did decently well on head and torso queries, but it suffered from a lack of engagement data on tail queries. So by using an LLM, similar to how we did for the product category classifier, we were able to generate very precise rewrites. In the example here, you can see that there's a substitute, a broad, and a synonymous rewrite. So for the case of avocado oil, a substitute is olive oil. A broader rewrite is healthy cooking oil, and a synonymous rewrite is just avocado extract. And again, just looking at the results from this, and we saw a bunch of offline improvements, and just moving from using third-party LLMs here, just going from more simpler models to better models improved the results quite a bit. This is based off of our human evaluation data. So as you can see, just improving the models itself improved the overall performance of the task. And in terms of online improvements, we actually saw a large drop in the number of queries without any results. This is pretty significant again, because we could now actually show results to users where they previously saw empty results, which was great for the business. So coming to the sort of the important part of this, which is how we actually scored and served the data. The thing is that Instacart has a pretty idiosyncratic query pattern. There's a very fat head and torso set of queries, and we have a sort of a long tail. So by pre-computing the outputs for all of the head and torso queries offline in a batch mode, we were able to sort of cache all of this data. And then at online, when a query comes in, we could just serve it off of the cache with very low impact on latency and fall back to our existing models for the long tail of queries. And again, this worked really well because it didn't impact our latency, while it greatly improved our coverage for the long tail of queries. Now for the really long tail where I said we would fall back to our existing models, we're actually trying to replace them with a distilled Llama 8B model so that we can actually do a much better job compared to the existing models. So yeah, to sort of summarize, essentially what we saw was that from a query understanding perspective, we have a bunch of models and just using our hybrid approach greatly improved their performance. But what's actually more interesting is that today query understanding consists of a bunch of models. And as Yezu was talking about in the Netflix talk, managing all of these models is actually complex from a system perspective. So consolidating all of these into an SLM or maybe a large language model can make the results a lot more consistent. And I'll finish it off by giving an example here. There's a query hum that we sort of saw some interesting issues with, which is spelled HUMM. The actual query, our query brand tagger identified the brand correctly as a brand of kombucha, but then our spell corrector unfortunately corrected it as hummus. So the results were really confusing to users and was pretty bad. But by using a more unified model, I think the results were much better. The second is by using an LLM for query understanding, we can actually pass in extra context. So instead of just generating results for that query in isolation, we can really try to understand what the customer's mission is. So for example, detect if they're actually here to buy ingredients for a recipe, etc. And then generate the content for that. So to talk more about that, I have Tejasvi here.
Thank you, Anish. Now I'll quickly talk about how we used LLMs for showing more discovery-oriented content in search results page. Just to restate the problem, our users found that while our search engine was very good at showing exactly the results that they exactly wanted to see, once they added an item to the cart, they couldn't do anything useful with the search results page. They either had to do like another search or go to another page to fulfill their next intent to some sorts. Solving this with traditional methods would require like a lot of feature engineering or manual work. LLMs solve this problem for us, and I will talk about how. So this is how it looked in the end. So for queries like swordfish, let's say there are no exact results. We used LLMs to generate substitute results like other seafood alternatives, meaty fish like tilapia and whatnot. And similarly for queries like sushi, where there were a lot of exact results, let's say, we would show at the bottom of the search results page, we would show things like Asian cooking ingredients or Japanese drinks and so on in order to get the users to engage. I'll talk about the techniques here, but both of these discovery-oriented results we saw led to improvement in engagement as well as improvement in revenue for each search. Cool. Like I said, I'll get into the techniques, but let's first talk about the requirements to generate such content. First, obviously, we wanted to generate content that is incremental to the current solutions. We don't want duplicates to what we were already showing. And the second requirement, and the most important one, is we wanted all of the LLM answers or the generation to be aligned with Instacart's domain knowledge. What does this mean? So if a user searches for a query called dishes, LLM should understand that it refers to cookware and not food, and vice versa for a query like Thanksgiving dishes, right? So with these requirements in mind, we started with a very basic generation approach. So what did we do? We took the query and we told the LLM, hey, you are an AI assistant and your job is to generate 2 shopping lists. One is a list of complementary items and another is a list of substitute items for a given query, right? Looked good. So we saw the results, they looked pretty good. Our PMs vetted everything, we looked at everything. And like Vinesh said in QU, when we launched this to our users, we saw that the results were good, but users weren't engaging it as much as we would have liked it to. So we went back to the drawing board and we were we tried to analyze what was going on. And what we realized quickly was, while LLM's answers were common sense answers and so on and such, they weren't really what users were looking for. Taking the protein example again, like users, when they search for protein, they look for protein bars and protein shakes rather than what LLM would give as an answer, which is chicken, turkey, and tofu and whatnot, right? So what we did was we augmented the prompt with Instacart domain knowledge. So in one case, what we did was we took the query and then we augmented it with like, here is the query and here are the top converting categories for this particular query, along with any annotations from the query understanding model, like, hey, here is a brand present in the query, here is like a dietary attribute present in the query, and so on and such. In another case, we were like, here is the query, and here are the subsequent queries that users did once they issued this particular query. So once you augmented the prompt with this additional metadata about how Instacart users behave, the results were far more better. I don't have the time to show like the before and after, but like I said, we definitely saw like a huge improvement in both engagement as well as revenue. I'll quickly talk about like how we served all of these contents, like very similar to QU. It's impractical to call the LLM in real time because of latency and maybe cost concerns sometimes. So what we did was we took all of our historical search logs. We called LLM in like a batch mode and stored everything. So query, content metadata, along with even the products that could potentially show up in the carousel. And online, it's just a very quick lookup from a feature store. And that's how we were able to like serve all of these recommendations in like blazing fast time. Again, things weren't as simple as we making them out to be. Like Vinesh said, the overall concept is simple. The prompt itself is very simple. But there were 3 key challenges that we solved along the way. One is aligning generation with business metrics like revenue. This was very important to see like top line wins. So we iterated over the prompts and the kind of metadata that we would feed to the LLM in order to achieve this. Second, we spent a lot of time on ranking, on improving the ranking of the content itself and so on and such. So our traditional PCTR, PCVR models did not work, so we had to like employ strategies like diversity-based re-ranking and so on and so forth to get users to engage with the content. And then the third thing is evaluating the content itself. So one is making sure that, hey, whatever LLM is giving is one, right, it's not hallucinating something. And second, it adhered to like what Instacart or what we need as a product, right? Cool. So summarizing the key takeaways from our talk, LLM's world knowledge was super important to improve query understanding predictions, especially for the tail queries. While LLMs were super helpful, we really found success by combining the domain knowledge of Instacart with LLMs in order to see the top line wins that we saw. And the third and the last one is evaluating the content as well as the query predictions and so on and such was far more important and far more difficult than we anticipated. We used LLMs as a judge in order to make this happen, but very, very important step. And we realized that kind of late. So yeah, that's all from us. We'll take questions now.
Thank you, Tejasri, Vinesh. Yeah, we'll take questions at the mic while the next speaker gets set up.
Hi, thanks for the talk. Have you also been trying around queries which are very long in natural language? Like, I want these 3 items and these 5 items, like what we would do it on ChatGPT? Or it's still like single item, that's the focus?
Yeah, I think we have actually launched something in the past, like Ask Instacart, if you may have heard of it, which essentially takes natural language queries and tries to map that to search intent. So for example, you might say healthy foods for a 3-year-old baby or something like that. And so that would map to things like fruit slices. I don't know if 3-year-old toddlers can eat popcorn, but something along those lines. And then we had our usual ranking, recall and ranking stack sort of retrieve those results.
So any learnings from that experiment for you?
Yeah, so I think we actually have a lot of learnings from that. Essentially, as this we already mentioned, we need to inject a lot of Instacart context into the model to be able to get decent results. The evaluation part is really key. So having a robust automated evaluation pipeline was important. And lastly, passing context. That is, for example, if it's let's say it's a Mother's Day query, and let's say we come up with individual search intents as perfumes, you really want women's perfumes to be in there. Whereas when we just had perfumes, we could see all kinds of items. So passing that context from the LLM to the downstream systems is really important.
Thanks.
Yeah, we have a lot of examples where we failed. We can talk about.
Thank you. I'm sorry, I don't think we have time for any more questions, but we have our last speaker, and then right after that, the speakers will be hanging around. So thank you, Trajastri and Vinesh again.
Thank you.
Finally, we have Devansh, Principal Product Manager at Google. He'll be sharing with us how they adapted a Gemini checkpoint for YouTube recommendations. He also shared about how they built Semantic IDs that we've heard a lot so much in this track that distill multimodal features into tokens. Take it away, Devansh.
Wonderful. I guess while we get the slides up, I can just introduce myself. I'm Devansh. I'm a product manager at YouTube. I've been working on recommendation systems at Google for a while and built a new recommendation system across DeepMind and YouTube that uses Gemini to recommend YouTube videos. And so I just want to take you through the process of how we built that with a lot of examples and share a recipe of how you might build this kind of LLM-based recommendation system. I'll just get started without some of the slides. Here's why I think this is important, right? I think there's a lot of attention in terms of how LLMs are going to transform search. Google search is having a revolution. ChatGPT has a big chat interface. Perplexity is a product that a lot of people use. But I think recommendations is probably a bigger problem that is underhyped because it's kind of transparent to the user. And I think the application of LLMs to recommendations is going to be a bigger consumer application than search. So in terms of my talk, I just want to introduce the problem of YouTube recommendations and then talk about how we've built large recommender models. We're adapting Gemini for YouTube, how we built Semantic ID and how we're using that, and then end with this recipe of how you might use an LLM to make a recommendation system. To start, why this is important. Who here watches YouTube every day? It's one of the biggest consumer apps in the world. And a large majority of the watch time on YouTube is driven by the recommendation system. And we serve recommendations across home, watch next. We have a big shorts product. And even a lot of our search results are personalized in some way. And so if you think about consumer applications of LLMs, I think in terms of consumer engagement and impact, recommendations is going to be a much bigger application than search is. And this is true of any consumer app with a billion DAU. The way I think about the recommendation problem is you're trying to learn this function of you get a user and their context as input, and you're trying to give them a bunch of recommendations. At YouTube, we have a bunch of user information like their demographics, their age, their gender, where they're located. We have a lot of context about them. What are the last 100 videos they watched? How deeply did they engage with them? What did they comment on? Who are they subscribed to? And we use all of that to make video recommendations. We've tried a lot of different modeling techniques here, multi-headed rankers, embedding models, sequence-to-sequence, transformers. There's a long history. And about 2 years ago, we started thinking, how can we rethink this recommendation system on top of Gemini, which has been making incredible progress in modeling? How can we adapt that for YouTube? And so we've built this system, which we call LRM, Large Recommender Model, where we adapt Gemini for recommendations. Okay. Okay. And so the way that we do this is, I guess I'll just pause for a second. Good? Yeah? Okay, cool. Okay, back to how we're adapting Gemini for recommendation tasks. So we start with this base Gemini checkpoint, and then we're adapting it for YouTube recommendations, teaching it a lot of information about YouTube to get this kind of unified YouTube-specific checkpoint of Gemini, which we call LRM. Then we can align it for different recommendation-related tasks like retrieval and ranking, and basically make a small custom version of this model for all of the major recommendation surfaces. And so this is a model that we have launched in production at YouTube for a while in terms of the retrieval system, and we're experimenting a lot on the ranking side. So I want to start with just kind of explaining how we built this YouTube and Gemini model, and then we'll talk about how we use it for retrieval. The first step of this kind of a model is you have to develop a way to tokenize videos. So when you, in terms of an LLM, when you give it an input, it tokenizes that text and then is predicting the next text token. The ideal product we wanted to make was we want to give this model an input of a number of video tokens, and then just get video tokens out that would be good recommendations. We had to build this because even with 1 million tokens of context, when you want to reason over many videos, you have to compress that video representation in some way. And before we kind of settled on this approach, we tried a bunch of other things like predicting search queries and retrieving videos through that, or trying to just recommend videos directly. And those solutions were just not good enough. And so we built Semantic ID, which we actually wrote a paper about last year, and it was presented at RecSys. The way that this Semantic ID works is you take a video, you extract a number of features out of it, like the title, description, transcript, even the audio and video frame level data. You put all of that into a multidimensional embedding, and then you quantize it using RQVAE to give every video a token. We've written a pretty detailed paper about this if people are interested. But at a high level, the way I think about this is we're making the atomic units for a new language of YouTube videos. Once we have these tokens, you can imagine the whole corpus of billions of videos on YouTube gets organized around these semantically meaningful tokens. And so you could imagine the first token representing topics like music, gaming, sports. Within sports, you would have different sports, and then you can get to volleyball. And so these two volleyball videos would share some tokens in the prefix, but also then have a unique identifier. And this, I think, in itself is an interesting milestone to move away from hash-based tokenization into a semantically meaningful one. And we use this in production at YouTube. What we then tried to do is this process of what we call continued pre-training, where we're trying to take this model and have it understand both English and this new YouTube language. And we do this in two big steps. One is around linking text and SID. And then the second step is around having it understand sequences of watches and be able to reason across this video space. And so some of the example training tasks that we're teaching this model, you have this video, it's a tennis highlights video, which has some semantic ID. And you can prompt it and say, hey, this video has title XYZ, and the model starts to learn to output the title. You could imagine a very similar thing where you could say, has creator or has topics, and so on. And so you're basically trying to connect text and this video token. Then what we can try to do is we have a corpus of all the YouTube engagement data, all the paths that users took through YouTube when they watch videos together. And you can prompt the model with things like a user has watched the following videos, A, B, C, D, and you mask some of those videos. And the model starts to learn to predict those masks. And now it's starting to understand what are videos that are watched together and make relationships between videos on the basis of user engagement, right? After a bunch of pre-training tasks like this, we get this really interesting model that can reason across English and YouTube videos. And so this is an example from a user's watch history. And we find that this model can now reason across these videos. So you could prompt it with things like, hey, video 1 is interesting to tennis fans because it's about Wimbledon. Video 2 is interesting for F1 because it's about the Spanish Grand Prix. Video 3 is interesting to math fans because it's about pi. and then you prompt video 4 is going to be interesting too, and the model starts to be able to understand that it's interesting technology fans because it's about AI. And this is just based on the semantic ID definition of a video. It doesn't really have a lot of other information to go off of. So I think this in itself is a very interesting checkpoint that is starting to reason across English and YouTube. Once we have this model, we think about how we can use this for different video recommendation tasks at YouTube. And the first one that we focused on is generative retrieval. And so here, you could just construct a prompt for every user and see what this model recommends. And so in this example, you have a user, they would be a 24-year-old woman in the US on Android. They're watching this highlight video from the Olympics, and they have some watch history of 50 videos they've watched in the past, how they engaged with it. And you can just construct a prompt like we have on the right with this user demographic information, the context video, and have the model decode some video recommendations as SIDs. We find that this gives really interesting, unique recommendations, especially for our hardest recommendation tasks. So in this example, when you're watching this highlight from the Olympics, the production system before LRM would give you other men's track races. Now with this new model, it's able to find this unique connection between the user demographic and their past watch history and find related women's races that we weren't able to recommend in the past. And so we find that, especially for users where we don't know as much about them, we get very interesting and unique recommendations out of this strategy. And so we've experimented with this and launched it in a few places at YouTube. The big findings from this is that LRM is a very powerful model, but it's really expensive to serve. It learns very quickly. It's very training data efficient, and it handles our toughest RecSys tasks. But the biggest limitation was that the serving costs are too high, especially for the scale that YouTube operates at with billions of users. And so after we got our first experiments working, we spent a lot of time just reducing the TPU serving cost. And we got 95% plus cost savings to be able to actually launch this in production. One other strategy that we used, which I think is kind of interesting, is we tried to turn this into an offline problem where it's the same prompt and the same model. We just remove the personalized aspects of this prompt. And we wanted to build just an offline recommendations table where if you're watching video A, what are the candidate videos that would be good to watch next? And normally, these unpersonalized recommendation models just don't hold a candle to a personalized recommender. But because this LRM is trained from a really big checkpoint, it actually gives us some differentiated recommendations. And so in the YouTube context, we can take our corpus of billions of videos, look at the head, which represent a lot of the watch time, do offline inference, make this offline RecSys table, and then we can just do a simple lookup to serve some recommendations. And so this was kind of a complete way around our serving problems. I want to talk a bit about the challenges for YouTube. And I think in some ways, making an LLM-based recommendation system is harder than training an LLM. One of the big differences is the vocabulary and size of the corpus, right? So for Gemini, if you're training an English LLM, your vocabulary is about 100,000 words in the Oxford Dictionary, and they add about 1,000 words every year. At YouTube, if you imagine the library of YouTube, it has billions of videos. We have 20 billion videos on YouTube, with millions added every day. And the freshness of videos is really important, much more so than LLMs. So if you think about a new word that's added to the English dictionary, word of 2023 was Riz. If your model Gemini doesn't know about Riz, it can still answer 99% of questions that people would have. Maybe it misses some jokes, maybe it misses some pop culture references. But in the world of YouTube, if Taylor Swift drops a new music video, you have to be able to recommend it within the next minutes or hours. Otherwise, a lot of users are going to be upset. So even within this large corpus, you have to very quickly understand what are the videos that are important and start recommending them to the right user. And so what we do with this LRM recommender is we have to continuously pre-train it on the order of days and hours, which is very different than classical LLM pre-training like Gemini, which happens maybe like once in 3 to 6 months. And so in that way, it's a much harder problem. And then the last part is scale. We have great models in Gemini. Gemini Pro is incredible, but there's no way that you can serve that to billions of daily active users. And so for YouTube, we had to focus on the smaller, more efficient models like Flash and even smaller checkpoints than that, just to be able to hit the latency and scale requirements that we have. So I kind of want to summarize the journey that we've been on YouTube in this, what I think of as a LLM and RecSys recipe that you can maybe adapt to your own application. And there's 3 major steps to this, right? The first is you want to find a way to tokenize your content. Just like LLMs tokenize text, you want to make some essence of your content into an atomic token. One way to do that, which we've done, is you find some rich representation, a bunch of features, build an embedding, and then find a way to tokenize or quantize it. And the outcome of this is like you're making your own domain-specific language. The second step is you then want to adapt the LLM and basically make links between English and your domain language, and find training tasks that help you reason across English and these new tokens you've built. And so the outcome after this step in my mind is it's a bilingual LLM that can speak English and natural language, but it can also speak your domain-specific language. And then once you have this, you can do the third step of prompting it with user information, where you can just construct personalized prompts with user demographic, user activity, different actions, and then train task-specific or surface-specific models. And you have a generative recommendation system on top of an LLM. And this is like a tweet-sized summary of maybe 2 years of work. Maybe the last thing that I want to talk about is kind of where I see this going, and some possible future directions for LLM and RecSys. I think the stage that we're at right now is that LLMs are just augmenting recommendations. They bring these magical recommendation experiences, they enhance the quality, but they're largely invisible to users. Like, your YouTube feed just got better, but you don't really know whether a Gemini inference happened or not. This is why I think the LLM application of RecSys is very underhyped, because users don't directly know what's happening. I think we're close to a world, and we're experimenting with this. If you have, like we talked about, a bilingual LLM across English and recommendations, users can then talk to it in natural language. And I think you're going to start to see experiences where users can steer recommendations to their own goals. The recommender can explain why a candidate was recommended to a user. And users can start to align it towards their own goals expressed in natural language. And I think also the lines between search and recommendation start to blur in this world. And then maybe a hint of the future is I think you're going to see recommendation and generative content start to come together in the future, where we're going to be recommending a personalized version of a piece of content. And in the future, instead of recommending content, we may even start creating it. And you can get to really interesting N-of-1 content that's generated for the user. I think we're a bit away from this, but it's going to come sooner than you expect with all the advances happening in AI. So yeah, thank you. I'll take any questions.
Thank you, Devansh. We have time for a few questions.
Hi, great talk. One question on generally how you balance the learning of the semantic ID embeddings within the model versus keeping the general language capability not damaged by learning through, for example, a tokenized user history, which is a very second language, very different from English. Any high-level takeaway that you can share?
That's a super interesting question. We've struggled with this a lot. In terms of some of our early applications, we mostly cared just about recommendation quality, in which case we over-indexed on speaking the semantic ID language. And as you overtrain on more and more of those examples, actually the model forgets to speak English. Maybe it's reasoning in some intermediate layers, which finally end up in semantic ID language. We are trying a bunch of things like, with mixture of experts, maybe we can have a few experts that retain the text capability while other experts focus on the semantic ID capability. And so it's a balance. And I think we're going to shift more towards text as we try to build these interactive experiences where text input from users is going to become more important.
Thank you.
So during this process, did you learn any good suggestions for cold starting embeddings on these domain-specific tokens?
Yeah, so one thing is semantic ID training process is entirely unsupervised.
Okay.
We're not telling, it's making its own quantization of the video corpus. When you sample to see what the model is doing, we find that it's learning concepts like sports versus movies and entertainment, but we didn't actually try to teach that explicitly, which I think is very interesting. I think the second aspect is, because of semantic ID, we can warm start into a semantically meaningful space. And what we find is performance for videos that were uploaded in the last day or the last week gets much better because we're better understanding this fresh and tail content.
Got it. Thank you.
Hey, quick question. So when you said you extract frames as part of making the semantic ID, are you just running a video at, let's say, 3 to 30 FPS, making a grid of them, running siglip or siglip2, and inserting that?
We're just trying to sample video frames. We've tried a few different approaches where maybe we try to sample from key moments in the video. We actually have the engagement data. If you've seen in the YouTube player, it can highlight what are the places where people had the most engagement. So we try to sample from there. Given the scale, we can't sample a lot of video frames, so we try to intelligently select it. But we do have video frames, and over time, I think we'll get more.
In this way of selecting it, are you able to highlight important things that are based on small objects in a video pretty well? Let's say there's a person in the distance that's of attention of this video.
Hard to say, because at the end, all of this video information gets compressed into 8 tokens. So it's probably learning something, but it's hard to know exactly what it picked up from that video frame. So it's unclear.
Thank you.
Yeah.
So, yeah, it was a pretty good talk. I have a question regarding pre-training. Okay. So did you also feed in a user query and what they watched also as a pre-training data? If yes, then did you also use semantic ID for user as well in pre-training, or just semantic ID is only for the videos?
Yeah, so in this case, we have only tokenized videos. And we focused more on sequences of watches rather than search query to what watch originated from that search query. You could imagine some parallel work where you try to tokenize users and build some kind of user token that represents the last 500 watches that they have had and so on. We've experimented with some stuff there. I think it's less far along. But yeah, I think it's a very interesting research direction to do.
So the pre-training was done on top of existing Gemini pre-trained model, right?
Yeah, we basically take a Gemini checkpoint and then adapt it for this YouTube purpose and get this YouTube and Gemini LRM checkpoint.
Okay. Yeah, so it would be cool to see semantic ID of videos to VO3,
Yeah.
Hey, I'm kind of curious, how much improvement do we see compared to the non-LLM or more traditional recommendation system? And when should we use a more traditional one, and when should we use LLM-based recommendation system?
Yeah, I can't really share metrics. I can share everything except code and metrics, And so we've given you as much conceptual steps of what we did. Maybe what I'll say is, I think it's been the biggest improvement to recommendation quality we've seen in the last few years. So I do think it's quite significant.
Thank you.
Well, please join me and give a big round of applause to all our speakers. So for all of these speakers, we actually reached out to them personally. They didn't submit any talks. We reached out to them because we know that their work was high quality, and I was really interested to share their work with you. Some of them are still hanging around. You can try to find them and just ask them as many questions as you have. Thank you everyone for joining, and I hope you have an awesome rest of the conference. Thank you.